just saw your text.
Thanks everybody for coming out this morning and your patience. We are resolving a technical difficulty with the streaming audio, so we're going to hold up here for a little bit longer. But thanks for being on time. Hope everybody had a great night. And hello streaming, are you there? Oh wow, just in time. So are we ready to go, taping and streaming team? Yes, maybe. Oh, wow, I see thumbs up. So, well, a couple of announcements for everybody this morning. This is the last day of ShmooCon, at least this year. We'd appreciate any of the feedback that you have on how we do things or what you would like to see improved for the future. We really appreciate that because that's the only way we can do this better. Please send us feedback to info@shmoocon.org. Would appreciate that. Also, please visit registration. You can pick up some previous year t-shirts and bags so that you can take them home. That means that we don't have to take them home, and as the truck driver, I really appreciate that. Lastly, I have a giveaway. It is a light. It has the ShmooCon logo on it. How long does it take light to get here from the sun?
8 minutes.
I heard an 8 minutes over there. I'm not throwing it. Okay, maybe I'll throw it. So, without any further ado, I'd like you all to please give a warm ShmooCon welcome to our first speakers of the morning, who are John Nunez and Jay Smith, with their talk, Mainframe Hacking for Kicks and Giggles.
Thank you everyone for being here. I know some of you were probably at LobbyCon late last night, and some of you might be hungover, so thank you for getting here early. As the slide says, this is a talk about... Oh. Testing. Oh, there we go. All right, thank you. So as the title of the talk suggests, this is about mainframe hacking, specifically around CICS applications. Most of the talks in this area have been around the system side, but this is primarily focused on the application side. So we have a few housekeeping items to cover before we really get going. The first one is that if you've never worked with mainframes, this is going to feel like drinking from a fire hose. That's how it felt for us. And due to that, we are not going to cover a lot of system level concepts. So we're not going to talk about ZOS, VTAM, JCL, none of that stuff. It's just mainframe overview and then specifically things around applications. This next one is that we are not mainframe experts. We're security researchers who were tasked with looking at mainframe applications and how they work. We didn't know anything about mainframes when we started this, so if you're an operator or a developer or a longtime user, please cut us some slack. We're not mainframe guys. We're hackers. And then the final one is a disclaimer that we're obligated to put by our employer, and it's just what it says. We are not here on behalf of or representing our employer, and anything that we say or do is our own views and not those of our employer. All right, with all that housekeeping out of the way, a little bit about the team. My name is Jay Smith. I've been doing IT for about 25 years. I've done everything from help desk to systems engineering, network engineering, NOC work, SOC work, development, and now I am a lead security researcher for my company. My current research focuses around mainframe systems, IVR systems, and MQ.
I'm John Nunez. I got my career started in software development, then information security compliance, eventually got into pen testing. Since then, I've specialized in web apps, API, pretty much anything HTTP, some mobile apps, and most recently, mainframe applications. We're excited to talk to you all about today.
And then the last member of our team, Garland, could not be here today, but his contributions were invaluable for reasons that we will get to later, so we want to make sure that he does get due credit for the research. All right, so before we start talking about the applications, we just want to level set about mainframes in general. So a show of hands, who here has worked with a mainframe as a developer, operator, user? Okay, a few of you. How many of those within the past 5 years? Not as many hands. All right, that sounds about right. And then how many people here have done a security assessment on a mainframe? Okay, a few. Some of the hands are the same, but not most. All right, and that's kind of the same boat we were in. We're just security guys who had to look at a mainframe. So for those who didn't raise your hand, when we say mainframe, this is often what people think. This legacy, archaic system, like a proverbial dinosaur of computing. I've talked to people and they'll say, hey, I used to work with those in the 80s or 90s, or those things are still around. Or maybe you think of this, like this giant machine that takes up this whole room and requires a team of people to operate, like Joshua from War Games. Well, the reality is that today they look like this. This is a Z16 mainframe, top of the line, just came out last year. It is one of the most powerful commercial computers you can buy. It runs anywhere from the high 6 to low 7 digits. And it runs a modern operating system known as ZOS, the most recent version of which came out last year. So this is modern hardware running a modern operating system. There is nothing legacy about this at all. And whether you realize it or not, you rely on these systems all the time for everything you do day to day. If you have withdrawn money from an ATM or paid for something with a credit card, if you scanned a check for a mobile deposit or booked a flight or paid your taxes, anything like that, you have relied upon a mainframe. They have been and continue to be the backbone of many industries that we rely on as society today. Industries such as finance and banking, healthcare, insurance, utilities, government, all of these industries could not work without mainframes. And there's a few reasons for that. The simple answer is they are very, very good at what they do. There is a reason that they command the price that they command. So a few examples of that. A modern mainframe can process roughly 19 billion encrypted transactions per day. To put that into some perspective, that's the equivalent of hundreds of Cyber Mondays per day per single machine. They have mean time between failures measured in decades and have uptime of years, also sometime of decades. You can take an application that was developed in the 70s or 80s and drop it on a modern ZOS system, and it's just going to run right out of the box with no issues. That's like taking a DOS or a Windows 3.1 application and running it on Windows 11. So these are very, very powerful and useful machines. And unfortunately, that makes them high-risk systems. It's not an exaggeration to say that if mainframes were to stop working today, for whatever reason, it would be global economic pandemonium. They are that critical to our infrastructure. And unfortunately, they are not tested often enough or thoroughly enough. When I asked the question about who here's done a security assessment, there was maybe 5 people in the whole room that raised their hands. And that should be way more. So now that we've level set, that's all we're going to talk about for the mainframe side. Now we're going to focus on the application side. Now the first thing to understand about mainframe applications is how they differ from a traditional distributed system. So let's say you have a web application. You probably have an application server, a database server, a logging server, an authentication server, and you have all of these disparate servers that are working together to support the operation of that application. Well, in a mainframe, everything is self-contained in the mainframe itself. There is no distributed components to it. It's all this monolithic machine that does everything in-house. And it does that through subsystems that are contained within the mainframe. Now, we can broadly categorize the applications into 2 camps. The first one is batch processing applications. So with these applications, you have some input, it goes through some kind of data transformation, and then you get some output. So if you're a regional sales manager and you want to consolidate the nightly reports for all of your regional stores, a batch process could do that. The time that these take is a function of the work to be done, and these can process terabytes of data. So you can have a batch process that runs for minutes, hours, or even days. And the key takeaway is that this is not something that an end user will submit and then get an immediate response back. This is something that is just either automatically kicked off or kicked off as a back-end process, and then it just runs until it's done. In contrast to that, you have online transaction processing, or OLTP. And this is the style that you're probably more familiar with. This is when an end user goes and does something and then gets an immediate response back. So I'm a loan officer and I want to look at this person's loan account information. I put in their account number, I immediately get a response back with their account information. I want to make changes to it, so the terms of the loan or contact information, whatever. I submit those, I immediately get a response back saying those changes have been saved. So the most common OLTP system is CICS, the Customer Information Control System. And this is actually a subsystem that supports the running of mainframe applications online. So this subsystem handles everything. It handles communication with all the other subsystems. It handles the management of shared resources. the integrity of the data, responding to each individual concurrent user. Basically, everything necessary to run this application is handled by the CICS subsystem. And you can think of these as web applications before the web. And it's a rough analogy, but it helps us understand some of the terminology used. So when you're working with a CICS application, the terminal is your web browser. So if you want to go to the CICS application, you're using a terminal. And there's a few other interfaces you can use, but primarily an end user is going to do it this way. Now, once you're on that CICS application, or once you're on the terminal, you need to know where you want to go. In a website, that would just be, you know, your URL, www.google.com. In a CICS application, that's your region. So you need to know what region you want to log into. So in the example here, DVCA prod is the region that we're logging into from our terminal. Well, then once you're logged in, you need to know where on that website you would want to go through. So for instance, using the Google analogy, /mail to get to your mail. Well, in a CICS application, that's known as your transaction. And it's a 4-character alphanumeric transaction ID. So once you log into your region, you would type in your transaction, and that's how you get to it. And you can go to any transaction that exists on that region, provided you have authorization to do so. Now, as I mentioned, there are multiple ways to interface with CICS. Most of these other ways are back-end processes utilized by front-end systems. So you have Java applets, web services, RPC calls, native mobile applications, all of these other ways for a front-end system to interface with CICS on the back end. And you may not realize it, but a lot of websites that you do use interface with CICS on the back end. So it's a very, very prevalent subsystem. Now, unfortunately, CICS applications suffer from this concept of a legacy code base with modern infrastructure. So I mentioned earlier that you can take an application that was developed in the 70s or 80s, drop it on a modern mainframe, and it's just going to run right out of the box. And that's fantastic for support or operations. It's terrible for security, because many of these applications were designed at a time where nobody was thinking about security. And we have talked to and met with developers who've said things like, the person who designed this retired 10 years ago. We're just kind of keeping it going along. We don't actually know how all this stuff works. Or we've seen applications that have not had a single code release in 10 plus years. So this is a very, very prevalent problem with these applications. Now I'm going to turn it over to John, who's going to talk a little bit about the testing side and our research.
Great. So at this point in our research, CICS became an obvious candidate for testing mainframe applications. But we ran into a number of challenges. I know we have some mainframe developers and operators here, so I don't mean to upset anyone, but mainframe developers can be difficult to deal with. Not all of them, of course, but due to fear of downtime, they are not going to be happy with you poking around their systems. And these systems can be easy to bring down, especially if you don't know what you're doing, which we know from experience.
Yeah, you get that call from a mainframe operator really quick when you bring down their system.
Yep. Another challenge was getting our hands on a mainframe for research. A ZOS license can cost thousands of dollars. Mainframe hardware can cost hundreds of thousands of dollars. IBM does have alternatives for development and testing, known as ZD&T, but a personal license costs $6,000, and this is for a year. A perpetual license costs closer to $13,000. They did have a learner's edition, but it's no longer available, so we're not going to get into that too much, but it was about $120 a year. It did require prerequisite courses or proof of 1 year as a mainframe engineer, and there was a backlog of about 6 to 12 months before you can actually purchase it. Another challenge was the lack of tooling. If you're testing a web application, you probably use Burp or all these other tools that we've come to depend on, but there are very few tools for mainframe testing. In fact, most of the tools that we experimented with were developed by just 3 researchers, Phil Young, Dominic White, and Ayub, the creator of CICS. These guys have done amazing work, so we want to make sure that we shout them out and give them credit before we get into our own research, and we'll have links to their GitHub repositories towards the end of the slides and in our Discord channel. Perhaps the biggest challenge was the massive learning curve. None of the major cybersecurity training and certification bodies offer content related to mainframe testing, so you're kind of on your own. And you might say, okay, I'll just read the docs, except when it comes to mainframe, this might mean reading through 50 years worth of documentation. Okay, so at this point we had 2 things going for us. We had no idea what we were doing and limited to no reference material. So we did some digging, and eventually came across the 3270 Data Stream Programmer's Reference. This was the official reference manual for developing 3270-based applications. It has since been, it's been out of print for decades. You can still find it online. IBM hosts it, and you can even find it used on eBay if you prefer a hard copy. I like to think of it as one of the first API specification documents, maybe ever. And it had everything we needed to start mounting attacks on CICS. And here's what we learned. So the CICS terminal, or the 3270 terminal, is a block mode terminal, which means anything you change on the screen is only sent back to the mainframe when you press an attention identifier key. So this can be any of one of 24 function keys, the enter key, the clear key, and we'll get into these more in a bit. See how you can click anywhere on the terminal and it doesn't matter if there's data, if there's a field, or if it's just some random empty spot? This is because each character position on the screen corresponds to a location in the screen buffer. I like to think of the screen buffer as the terminal's RAM, and it stores all the data that is displayed and instructions on how to display it. Traffic over the mainframe, traffic between the mainframe and the terminal occurs over the TN3270 protocol. And this was IBM's way of adapting to the prevalence of TCP/IP and personal computers, because before that, mainframes required the use of a dedicated terminal that was physically attached to the mainframe via coax. So IBM's solution was to wrap the 3270 data stream in Telnet and call it TN3270. This allowed for mainframes to be accessed over TCP/IP, and allowed for the terminal emulators that we use today on any PC. You can analyze this traffic in Wireshark just like you would any other protocol. In fact, it's not uncommon to discover sensitive information that's sent to the terminal but kept in hidden fields and never displayed. This was a step in the right direction, and it was interesting, but in order to make some of the more interesting test cases possible, we needed a deeper understanding of the 3270 protocol. Fortunately, it didn't take much to get there, and everything we needed was in chapter 4 of the reference manual. All right, so there's two characteristics of the 3270 data stream that started to make some of the more interesting test cases possible: orders and field attributes. An order is an instruction or a command that we send to the terminal, like, this is a field, and this is where I want you to position that field on the screen. Each order corresponds to a specific byte value. So in this example, we see that the first byte is equal to the hex value 11. So we know it's a set buffer address order. And as the name implies, this sets a field's location in the screen buffer and as a result on the screen itself. The 2 bytes that follow are just parameters to the set buffer address order that specify the exact location on the screen. But the one we were interested in was the start field order, because not only does this indicate the start of a new field, it also indicates the start of a field attribute, which is the byte right next to it, and it's always the byte right next to it, according to the reference manual. There are other orders that can specify the start of a new field, like the start field extended, but the way we parse the attributes change. So the byte right next to it tells you how many how many key value pairs there are, and the second and third bytes would be the key value pair for that attribute. We're going to focus on the start field order and the field attribute byte. So I'm going to draw a comparison to a technology we're all familiar with, just to continue that analogy. I like to think of the start field order as an HTML input tag, and the field attribute bytes as HTML attributes for disabling and hiding an input tag. So to continue that analogy, whereas a browser renders HTML that's transferred over HTTP, a terminal renders the 3270 data stream that's transferred over TN3270. And hopefully this starts to make things click for you. All right, so we're going to focus in on the field attribute byte. Each highlighted bit in this byte has something to say about how that field is displayed or rendered. The bit in position 2 determines whether the field is protected or unprotected. In other words, can a user make changes to it in the display? The bit in position 3 determines whether a field is alphanumeric or numeric. And the bits in positions 4 and 5 work together to determine whether a field is hidden or displayed. We were particularly interested in bits 2, 4, and 5, because if we could intercept this traffic and flip these bits so that protected fields become unprotected and hidden fields become visible, then we would have viable test cases for testing mainframe applications. And we're here today because it worked. Because it worked. All right. So we even have some bonus attacks. So not only are we disabling field protections and discovering sensitive information in hidden fields, we're also brute forcing application level secrets and enumerating through all the known attention identifier keys. So before we get into our demo, I should mention that the 3270 terminal is incredibly finicky, especially if you're running it in a Docker container that's also in a VM. So we knew it would be a bad idea to do a live demo, but we're going to do it anyway, so wish us luck.
We're going to try. So before we get started with the demo, just to set some background on what we're using. So traditionally, this kind of research was done via what's known as MVS 3.8. So the ZOS license is generally unattainable for individual researchers for reasons that John enumerated on, but you can use MVS 3.8, which is a precursor to ZOS. It is perfectly legal to use, there is no problems, you won't get in trouble, and there's many ways of getting it. It can be run in an emulator known as the Hercules emulator. Now, when people are first starting to do this, what I always recommend is to use the TK4, that's the Turnkey 4 system, which is basically all of this stuff just packaged together in a single file. You just unzip it, launch it, you're up and running. There is also, in my opinion, a better menu than what comes with it by default, known as ISPF. That second link at the bottom is a Docker container I created that has all of this packaged with ISPF, and you can just download the Docker container and you're up and running with your own mainframe. The thing is, though, this is geared more towards just learning how mainframes work. It has nothing to do with security testing at all. So we worked with Soldier of Fortran, who some of you may know, and he released DVCA, which is Damn Vulnerable CICS Application. And it's exactly what it sounds like. It is an intentionally vulnerable CICS application for you to just go crazy with. It is a Docker container, so it's just a matter of pulling the Docker container, exposing 3270 to the host machine, and you're up and running in less than 5 minutes. And that's what we're going to run this demo on. And then the other thing that we want to talk about is the CICS pen testing toolkit. So this is our toolkit that was developed for testing CICS applications. When I mentioned earlier that Garland was an integral part to our research, this is why. He was the one that developed this tool, and he did it over just a few days because he's insane. It's developed in Python, and it basically acts as a proxy for C3270 or X3270. It allows you to intercept based on specific field attributes that John talked about, so sort of like burp, where you can just determine what you want to intercept on. It does have logging capabilities, but it's also very much in an early phase. So this is more a preview of what we're working on. We're working on releasing this tool, that's our plan, but as John mentioned, things are very finicky, so we're not doing it yet, but we are going to try and demo the tool as is. All right, so can you hear me on this? Can you hear me on this? All right, cool.
What's up?
All right. So right now, this is just a Kali VM, and we're running Docker. So we're running the DVCA image in a Docker container. So what we're going to do is we're going to start our CICS pen testing toolkit, and basically we just tell it the IP address of the mainframe server we're trying to connect to.
Pull it closer to your face and try to put it where you're talking.
All right. Oh, there. Okay, there we go. Sorry. All right. You just point the IP address to your mainframe. Since this is a Docker container on localhost, it's just 127.0.0.1. And you can see here that it's waiting for the connection. So it's now acting as a proxy, waiting for you to connect to it so it can send your traffic to your mainframe. So now we're going to launch C3270 and route it through the tool. Whoops. Sorry, wrong port. All right, so now you see that it's detected that we have connected to the tool. And this is the equivalent of burp where its intercept is on, so it's waiting for you to click on something. So we click to continue. Now we're logged into the mainframe Docker container going through the tool. And this is Soldier of Fortran's DVCA tool.
So when you go, you just type in DVCA, and you can see here that it's going to launch the CICS application automatically. You don't have to do anything. And then now that CICS application is up and running. So we clear our screen, we go to our transaction, and this is our vulnerable application. All right? So again, we are going through our proxy tool to access this container. And all of this stuff at the top, this is the tool. Now I'm just going to do a quick walkthrough of the application itself, and then John's going to talk about the hacking part of it. So this is just an office supply program. It's something that exists in pretty much any sales system. You know, it's just used for shipping and receiving. So we go into the first menu, we just see office supplies. So you have 3-hole puncher paper. You can get Dom Perignon for $85,000. 24K gold MacBook Pro, or a haunted idol. So a lot of you know, things in here to order. Then we have the shipping address. So this is the address of the customer. The idea being there's this supervisor code down here. So the idea is that you don't want just any random person changing the shipping address to their address and then ordering a bunch of stuff. So you need an authorization code to make that change. So if we try and make these changes, we get this invalid supervisor code because we don't know what the code is. And then the last one is the order history, which is just what it sounds like. This is the items that have been ordered since the container was built. All right. And now I will turn it over to John, who will demonstrate the tool.
Fingers crossed. Okay. So our tool is up here on the top. We have 4 tabs currently. A lot of the functionality is still under development. The key functionality being the hack field attribute. So as I mentioned, we're effectively intercepting the field orders or the orders in the 3270 data stream. I mean, that would correspond to the field type. So here's the start field order, the start field extended, and so on. And then we have here, we can choose between the specific bits in that field attribute byte. So we can choose to disable field protection. We can choose to enable hidden fields. We can also choose to remove numeric only restrictions. And we toggle that by clicking on the hack fields button. We have an inject to fields tab, which allows us to perform brute force or automated attacks. So you can select a payload list using the file key here or button. We can set up that payload list, and then we can run the injection. We can also choose a mask character to identify the exact field that we want to target, and I'll demo that in a bit.
You can think of this as the intruder tab in Burp.
Right. Remember I mentioned that the terminal emulator is a block mode terminal, and it only sends data to the mainframe if an attention identifier key is pressed. These are all of the known attention identifier keys, and what send keys will do is it'll automatically send all of these attention identifier keys in hopes of discovering hidden functionality. And it's not a stretch of the imagination to think that a mainframe developer, decades ago would have hidden functionality in some of these obscure 8 keys, especially today where we don't have 24 function keys on a modern keyboard. And not so much out of malicious intent, possibly just to facilitate maintenance in production. And then we do have, the tool does have extensive logging capabilities. We'll go through that after our first test case. So let's start the demo. All right, so the first thing I'm going to do is I'll change the shipping address. Let's go into menu option 2. So as Jay mentioned, I try to submit a change. It doesn't allow us because we don't have a valid supervisor code. So I'm going to go ahead and make some changes. Doesn't really matter. Okay. Let's not send that to Canada. Yes, okay. So again, I try to submit the change, doesn't work. We don't have a valid supervisor code. I'll try some common options, 1111, doesn't work. 1234, doesn't work. All right, so we have some options. We can go into our Inject into Fields tab. I'll select a payload list. It's just a word list of all possible permutations for a 4-digit code. So you would have 10,000 different options there. So I'll select the payload. I'll then select our mask character, which will use a $sign. I'll click Setup. So now the tool is ready to identify that mask character and know which field we're attempting to target. So I'll submit a test transaction with the mask with the mask character. And now we see that the tool found the field. So I'll go ahead and click Inject. And now we're iterating through every possible supervisor code in hopes of finding one that works. And we can see that up here on the left. Okay, so we're at 20. And I think we shortened this to about 50. Yeah, so just to make things easier. This can take anywhere up to an hour depending on how long your payload list is. Okay, so there we go. We found a valid supervisor code, and the valid supervisor code was 1337. So I'm going to go back to the main screen. Okay, I'll go back in to make sure that our changes persisted, and there we go. We were able to submit an address change by brute forcing a supervisor code. And these types of attacks are incredibly common in CICS applications. So we'll go into our supplies menu option, and we see that we have the printer paper. I'm going to click F7 to go to the next one. We have, sorry, F8. We have, okay, we have 3-hole punched paper. We have, so as we mentioned, the terminal can be finicky. Yeah, all right. Okay, we have the bottle of rosé. We have the MacBook Pro, and we have an ancient golden idol that's haunted. Right, I'm going to try and purchase this ancient golden idol, and we see that it's denied. So we're going to go back into our Hack Fields tab and enable these fields in hopes that we find hidden fields on this screen. So I toggle it, and we see that there's this hidden purchasable field. I'll go ahead and toggle it again so we can see that. There's this hidden field, and what the tool is doing, it's intercepting that the traffic between the server and between the mainframe and the terminal, and it's flipping those field attribute byte bits. So I'm going to change this from N to yes. I'll submit, and we see that now we're able to purchase the ancient golden idol thanks to that hidden purchasable field. So I'll go back. Let's purchase the 24-karat MacBook Pro. I'm going to turn off the hacked fields just to demonstrate that without the hacked fields set to on, we can't make changes. Notice that it's X protected down here, meaning that these fields are protected. It does not allow for end users to change it. So I'll go ahead and toggle hacked fields. We have our disable field protections on. So now we should be able to go in, and despite these fields being protected, we should be able to make changes to them. So we'll change it from 20K to something more reasonable. Well, from $165 to $1. Purchasable is already set to yes, so we'll go ahead and try and purchase this. Submit, and we see that we were able to purchase the 24-karat MacBook Pro, ideally for $1. We'll go back. We'll celebrate with a bottle of rosé. Our hacked fields are set to on, so we should be able to modify this. Let's do $5. Okay, we changed the shipping cost from $250 to $5. I try to purchase it, and we get denied because purchasable is set to N, so we go in, change it to Y, and we were able to purchase the bottle of rosé. So we'll go back to the main screen now. Yep. Yeah.
This is what working with 3270 is like. And we get an add-in. Okay.
You want to try to spin it up again?
Yeah. Demo gods at their finest.
We almost got through it. There we go. All right, so we go back to, let's go to the order history and confirm that our changes or that our purchases were successful. And there we go. We have the ancient golden idol. We have the gold MacBook Pro that we purchased for $1. We have the bottle of rosé that we purchased for $5. So now we need to cover our tracks. We'll go back to the main menu. And we'll use the Hack Fields button again to see if there's anything hidden on the main screen. And we see that there's this Delete Order History menu option. It's set to 99, so I wonder what that'll do. We submit the menu option 99, and we see that we were able to delete 8 records from history. So we'll go into the history menu option to confirm. And ta-da, our tracks were covered. The audit trail of purchased items were deleted, or was deleted. Okay, so now let's do our last test case. Can you get closer to the microphone, please? Yep, we'll run through our last test case now. I'll go to the enumerating of attention identifier keys.
Now, you see we've specifically excluded PF1, PF3, and PF5 because those are valid function keys to navigate through the application, and we don't want it to be moving through everything while it's enumerating.
Otherwise, it would be jumping through screens left and right. So we're going to go ahead, press Send Keys. And now notice that we're iterating through all the known attention identifier keys, again, in hopes of finding hidden functionality. So we'll let that run for a second. It shouldn't take long. Okay, and eventually we found a hidden attention or a hidden screen corresponding to a hidden attention identifier key. But if we want to see what key it was, we do have, again, the extensive logging capabilities. Here we see all of the attacks that we ran, effectively everything we've sent to and from the mainframe. I'll go to the last attacks here. Okay, so every time we toggle the hack fields, we'll see exactly what the settings were. So if we had remove field protection enabled or show hidden fields enabled, we'll see exactly what our settings were. And then down here, we'll see the EPSIDIC encoded payload that's sent to the terminal. And notice that when I toggle between, let me see, I did all of that. When I toggle between the log items, I'll see in the terminal the exact screen that invoked. Okay, so it's sending that payload to the terminal every time we click each log item. So go to the last bit just to demonstrate the attention identifier keys. So everything we've done through the demo.
And it saves all of this in a project file. You can pass in a parameter to change the project file, but this is all actually saved in the folder of the tool, so you can always reference it later.
Yeah. So in the last few log items here, we see the attention identifiers that were sent, so we can just scroll through them until we see which attention identifier was responsible for invoking the hidden screen. In this case, it was the PA3, and it can also be invoked by sending the sysrec attention identifier. And I think that wraps up our demo. We were able to get through it.
Thank you. All right, so some closing thoughts, because I know that we covered a lot of stuff. The first thing that we want to discuss are mitigating these. There do exist a few mitigations. So the first one, IBM has a 3270 IDS. And we do recommend that you use it, but with the caveat that it can't detect malicious traffic from anomalies.
It just goes, this isn't what we expected, so you'll have to fine tune it and play with it. It's not perfect. The next one is don't use application level authorization or authentication. You should be using system level stuff like RACF, Top Secret, ACF2. Just don't rely on application level. And unfortunately, a lot of these applications, again, were designed in the 70s and 80s, and you couldn't do this kind of thing back then. You were on a physical 3270 terminal, so they just didn't even think about this stuff. Don't hide, just don't use hidden fields really anymore, because anything that's hidden, we can just see it. Doesn't matter what it is, it's easy to see. And then you want to secure anything that you have within an attention identifier key. As John said, most of these weren't hidden out of malice or anything like that. It's just operators or developers would do it so they had an easy way to get back to something that they needed later on. But now we have the ability to enumerate through all of them relatively quickly. All right. So some key takeaways that we have for this. The first one is that mainframe computing is alive and well. It's not a dinosaur. It's one of the most important pieces of our modern infrastructure, and without it, like literally society as we know it would almost collapse. Like they are that important. The next one is that mainframe applications are not immune to security exploits. As we've demonstrated, these are not difficult attacks to exploit once you know how the protocol works and once you've developed a tool to work on them. We have seen every one of these attacks in real CICS applications. Like these are not theoretical. We have literally seen every one of these multiple times. And then finally, there are now resources available for you as a security researcher to do this kind of research, specifically the DVCA Docker container, which leads me into my next slide, which is a special thanks to Phil, a soldier of Fortran. His work was instrumental in us even finding our footing and getting started. He's been there to support us as a mentor. Like I said, he worked with us on the DVCA. He is, one of the mainframe gurus out there. He has, as far as I know, the only offensive security mainframe course out there, known as Evil Mainframe Training. He has given 10 plus years of talks on mainframe hacking, so you can just go to YouTube, look it up, see all of those talks. And then he also runs the Internet Mainframes Project, which is a Tumblr account that shows screenshots of internet-facing mainframes and CICS applications. So we're going to leave our contact information up here. As you can see, we created a Discord channel. I'm sure there's going to be questions, and a lot of this stuff gets complicated, as you might realize, so we may not be able to handle it during a Q&A. So feel free to join the Discord channel and ask any questions that you may have. But with that being said, thank you very much. So questions? Okay. Well, thank you.
Thanks, everyone.
Oh, yeah, sure. Yeah, oh, sorry. Yeah, my bad. I don't know, 50 or?
Over 20, certainly. I
more
would say
than-
about 50.
Yeah, probably closer to 50.
Yeah.
Yeah.
We've looked at about 50 CICS applications. The question was, how many CICS applications have we taken a look at?
Yeah, because
at
I
this
have a
point, it's-
follow-up to see if your sample set for the answer on the next one.
Yeah.
Right, it's been about 50 CICS applications, I would say, roughly.
Okay, out of those on the enumeration attacks, are you seeing at all that the developers were doing like a timeout or block because, oh, you hit N number, or no, because the assumptions of the environment at the time with fixed terminals?
I would have to assume it's the assumptions of the time, but no, we have never had anyone reach out to us or have problems with that or detect it.
And the applications never said like, oh, you're in a timeout period. That's all.
No,
That's
we never
amazing.
once had, we've generally been able to do this undetected. for the
And you
most
can
part.
just iterate away, and it's just like, yeah, keep trying, man.
Right.
Cool. Thank you.
Thank you.
Hi. I recognize that Telnet's kind of inherently insecure, but I was just wondering about, for just communicating over TCP, if there's any like new developments in like maybe wrapping the connection protocol in something else, or maybe securing Telnet in any way.
There is encryption, but the thing is we're man-in-the-middling ourselves, and it doesn't really matter. So one of the options in the tool, actually, when you start the tool, if you are connecting to a server that supports TLS, there's a flag that you can pass in, and we still can do the same thing with a TLS encrypted server. Because again, we're man-in-the-middling ourselves, so we're in full control. And that is something that we probably should mention, is that this is more of an insider attack. This is not something that somebody outside of your company is going to do, because even though there are a handful of CICS applications that have been internet facing, nearly all of them are internal only. So this is more of an insider threat kind of attack.
Okay, and for like outbound connections, you could just like wrap it in something else, I assume.
No, it's just TLS.
Oh,
yeah.
right. Okay.
And I believe one of Phil's talks, he mentioned that maybe half the mainframes he's worked with, he's actually seen that enabled. So it's still not enabled that frequently.
Oh, wow.
Even though he's been talking about this for 10 years.
Okay, thanks. Great talk.
Thank you. Okay. Was there anything from chat? All right. Well, thank you so much.
Thanks, everyone.
the 11 a.m. session of ShmooCon for Build It. A couple quick announcements. We couldn't do this without you, and we really appreciate your attendance and participation in the con. If you have any feedback or thoughts for us, please email info@shmoocon.org and let us know. We have some t-shirts and swag available still for donation and reg. And if you've lost anything, then we have a lost and found in reg as well to look for things. And Ted, who helps us by recording all the talks, has them available on SD cards at his table here in the hall. He does this every year for us, comes out and helps make sure that everything is captured. So if you want to take the talks home with you, you can stop by his table and buy them from him. So the talk that we have here for you now is called "It Must Be Nice to Have Washington on Your Side," and so I'll turn the remainder of the time over to the team from Johns Hopkins University in APL. So here we go.
Oh, right on. I'll say myself. We're a contractor to DARPA, so we don't speak for DARPA, but we'll be talking about kind of the program and you know, what we did under it. So just some background information, kind of the motivation that really Sergey Bratis, who is the PM that ran this program. Oh, I am very sorry. I should say on this slide before we get started, we also have in the audience Jen Spiro, who did a whole bunch of work on our on the project. Thank you, Jen. And we also made a lot of use of Paolo Gentry, was a intern who's not here today, but we are also indebted to them for the work on the project. So thank you, Jen, and thank you, Paolo. So the motivation for this is kind of some questions around why, you know, we've made a lot of progress in computer security in kind of the enterprise space and even smartphones and things like that. If you think about what things were like, you know, 15 years ago to now in terms of, you know, just antivirus patching, things like that. Whereas those gains really haven't materialized in the embedded device world. The embedded device world is still kind of like the Wild West of security. We also have we still have a big gap between the traditional software development world and the reverse engineering world. So we kind of live in the reverse engineering world. In the reverse engineering world, you usually spend a lot of time in your disassembly tools in Ghidra, Binary Ninja, IDA Pro, and you kind of make your databases, and maybe, you know, you use some of that information to patch some software or something like that, but you're not really able to feed that back to the software development community. And so these things were in Sergey's mind when he kind of kicked off this program. How do we bridge that gap between the RE and embedded development worlds in order to make some progress in security? So I'm going to be talking about AMP and what it is, the larger DARPA program. We're just a small part of that. Going to be talking about what we did on this project previously, Code Cut. Robert's going to talk about Deep Cut, which is a new machine learning approach to the Code Cut problem. Amanda's going to give talk about Code Cut and give a demo. Josh is going to talk about unlinking binaries, and Jonah's going to talk about recompilable C. This is just a little bit about who we are. I'm not going to read this all off, but basically we represent kind of a broad spectrum of groups at APL. So one of the great things about APL is that we kind of bring groups from like a wide variety of expertise to you know, solve these challenges. So we have kind of folks that work in RE, vulnerability analysis, We definitely work in embedded development and binary patching, and then we're also bringing in, Robert especially represents kind of the machine learning expertise. So we're able to pull these things together to solve problems, which is really cool. On AMP, so AMP is a large program. There are 8 different teams and then 1 team that does testing and verification. So I mentioned Dr. Sergey Bradis is the PM. We're part of the MineSite team, so we're actually a subcontractor to Siemens. And yeah, I mentioned there's 2 technical areas. Point of that is if you are kind of interested in this problem of embedded systems binary patching, but you're like, okay, I have that problem, but I don't really like your solution or what you're talking about. There's a whole lot of other stuff going on AMP, so you should definitely talk to us, and we can get you talking to Sergey to hear about all the other stuff that's going on. This is a picture of AMP and kind of what AMP is trying to solve in terms of embedded binary patching and how we fit in. So on the top, you see kind of your traditional build process for an embedded system. You have kind of a bunch of source files. You compile them into object files here. You link them, and then you get a single binary firmware blob. There's a satellite here because that's one of the kind of interesting, NASA is one of the government sponsors. They're very interested in this because they have satellites where they may have lost the source code, or they may still have the source code, but just the build tools are just so outdated that they don't really have a build chain anymore. They also want to be able to make as small a patch as possible. They don't want to have to like reload the entire firmware. They want to be able to like do a very small firmware diff. So the envision process in AMP, people are kind of tackling this a lot of different ways, but our team is looking at it as taking apart the firmware, so taking this fully linked binary and breaking it into object files, and then unlinking, which is really kind of a new concept, and Josh is going to talk about his work there. So to recover object files out of a linked binary, decompile them, patch, recompile, and then push that patch. Where the split in AMP is some teams are working on the targeted decompilation problem, and then there's a whole other set of teams working on the patching problem. So we're not really working on the part of applying the patch and verify that it works, but there's a whole set of teams working on that. So we're mainly talking about code cut today and a little bit about unlinking here. So we've been working on this for a little while, and I actually spoke at ShmooCon 2019 when and I had an initial breakthrough. We kind of spun our wheels in this problem for a while. The code cut problem, trying to recover the object file boundaries within a binary, is something that if you've been reversing for a while, you kind of know this intuitively. You probably kind of do it without necessarily even thinking about it, but doing it in kind of an automated way has been like a difficult problem. We even had Robert work on it as an intern. He got some. I'm sorry. They had some. I guess you would say graph algorithms that were kind of working, and now that they're back as a full-time employee and got this team together, they put together a really awesome machine learning solution to the problem. So we're going to talk about that in a sec. We had an initial prototype for IDAPRO. It was like not not great.
Robert's also going to talk about the limitations of how not great it was. In the meantime, we developed a thing called All-Star, which is our data set for testing. And so in 2021, we joined the Siemens Mine site team and got some funding to work on this. So I'll kick it over to Robert here.
All right. Well, we're doing something. So thanks for the introduction, Ozzy. So so the code cut problem that we're looking. Pardon? Better? Oh yes. All right. So the code cut problem that we're looking at is trying to take a compiled executable, mainly firmware, and trying to recover clusters of related functions. And so really we're trying to see, can we recover the original object files, the compiled units during the build process? So our approach to this is really informed by the original algorithm we had to this a few years ago, which relied on the insight that that function calls are actually pretty correlated to this module division, to this division into object files, and it's really that if all of the functions in an object file are vaguely related, then they should have similar calling patterns. So they should either be calling similar or the same functions, or really that they should be calling other functions in the same module a lot more so than they're calling just functions from different modules. So you should really be able to split most of these function calls into either library calls or calls to other functions in the same module. So the original algorithm for code cut tried to use some signal processing heuristics to identify like a change in directionality. So the idea being that if most of the function calls are to other functions in the same module, then because object files are contiguous in memory, when you near the boundary, the beginning or end of an object file, there should be a change in directionality. If you're at a function near the end of the object file, most of the calls should be going upwards. But when you start the beginning of the next object file, most of the function calls should be then going downwards. And so there's some sort of signal processing problem here, and the original code cut algorithm used some signal processing heuristics to analyze these function calls and try and guess where these boundaries between object files are. And it sort of worked. It didn't work great. It's definitely picking up on a signal, but there was quite a bit. But it was quite a noisy problem, and it wasn't all that accurate. So our motivation going in is that we wanted to use more powerful tools to better extract the module divisions. So we really are trying to view this as the function calls, the function call graph is what's going to be informing our guess at the division of the executable into object files. And so the most powerful tool we can apply to that is graph-based machine learning. And then we also wanted to make use of some more principled graph theory algorithms as opposed to this signal processing heuristic. So the main tool that we're using is graph neural networks, and they are pretty much a direct analog of convolutional neural networks, which have achieved a truly incredible accuracy for machine learning on image-based data. And so the main convolution step of a convolutional neural network, it aggregates data from neighboring pixels at each step and combines that with some nonlinear activation function and magical linear algebra. And when we want to adapt this to data defined on a graph on a network, then the natural step is that the convolution operation is aggregating data from neighboring nodes instead of neighboring pixels. Once you have this generalized convolution step, then you can just plug it in into your favorite machine learning framework. Here we used PyTorch Geometric, and really go to town. So one remaining difficulty of trying to use graph-based machine learning for this code-cut module division problem is that usually graph neural networks are trying to predict properties of individual nodes, or maybe of the graph as a whole. But we're instead trying to do this this clustering property. We're trying to find, we're trying to partition the graph. And there are some ways that you can try and force this into like into a node level prediction problem, but none of them are that good, or a particularly good fit for a problem. So we went back to the original code cut motivation, which is that the function calls, the edges connecting the nodes, should really be what's informing our prediction of these object file categories. So we trained the graph neural network to predict which function calls are between two functions in the same module versus two functions in different modules. And so you can convince yourself that this is really equivalent information to the module assignments to a proper object file partition. But it's substantially easier for the graph neural network to learn. And so this is because it's really a local prediction. You aren't asking the machine learning magic to predict something for all of the functions. It's really just predicting a two-option classification of each individual node. And so you can't have machine learning without an ungodly amount of data. And so to do this, we made use of the All-Star dataset, assembled labeled library for static analysis research, which is a fancy way of saying we took every Debian package ever, and took all of the compile and build information for each package. And so if we after filtering through this, we are looking at since our end goal is looking at trying to reconstruct the object file boundaries. We're only interested in packages which actually have a decent number of different object files in them. But we end up with around 80,000 different executables. And so we can extract the function call graph from each of these packages, and for training we could annotate it with some simple metadata about each function. And of course, we only want to actually make use of features which would still be present in strict executables. And so we're only using information like how big is your function in bytes? For each function call, what's the distance in address space between the source and target? But now that we have a machine learning model and a massive amount of data, we can plug it in and press play. But we do have one remaining issue. That does sound much better. We do have one remaining issue, that the graph neural network is is not directly predicting any object file boundaries. It's trying to classify every single function call with the confidence that this function call, the source and target are in the same module, the same object file. And so there's a big problem here, and that's that since we're just relying on machine learning magic, there's no guarantee that the output is consistent. As an example of what could go wrong, the machine learning output could say that function pairs A and B, as well as B and C, are in the same module, but that A and C are in different modules. And there's just no way to fully reconcile this. So we need to give our best attempt at reconciling all of these predictions to try and get discrete clusters of functions, to try and get a discrete set of object files. And so the tool that we use is taken from computational social science, specifically working at the graph's modularity. And so computational social science has quite a lot of problems which look at, I have an actual real-life social network, and I'm trying to figure out what are the actual friend groups and the like. And so one tool that's been applied is modularity, which is measuring the fraction of connections which are within a single module versus which are between modules. And so then we wanted to take the input function call graph, weight it according to the output of machine learning, and then try and figure out what is the partition which gives the optimal possible weighted modularity score. And so that's just going to hopefully correspond to the original object file boundaries. So we also get a bit lucky in this problem, in that we have a bit of extra structure that's not usually available in graphs, and it's that all of the object files are contiguous in memory, unless you're doing something very weird. And so this is then a bit of a easier problem than finding community structure in general, and we can make use of these two different types of structure. That there's the contiguous in memory structure, and then there's this function call graph structure. So we can combine those to efficiently determine the optimal partition. And when we glue all this together, we find that it works pretty well. The machine learning component gets a 97% accuracy. Ooh, that's not good. It gets a 97% accuracy at classifying the function calls as between two modules versus within one module. And so this doesn't translate directly to a 97% accuracy on the entire code cut problem. In fact, we find our accuracy drops a little bit to a 93% accuracy at predicting these object file boundaries, but it gets most of the job done. So there's maybe some more room for improvement in specifically the reconciliation algorithm, but this is a pretty good solution to the problem, and it achieves around a 7-fold improvement over the original approach to code cut, which was again based on signal processing heuristics. And with that, turn it over to Amanda.
So that was our. That was the theory portion of the of the talk here. So now we're going to get practical, talk about how we implemented it in Ghidra, which you can you'll be able to download here after the talk. And so Amanda's going to talk about that.
Okay, so I'm going to talk about the code cut and deep cut plugins that we developed for Ghidra. So again, the code cut goal is decompilation for a single object file by identifying object file boundaries in a linked binary. And the goal of the GUI is to allow users to really take those deep cut Is that better? Okay. Take those deep cut results and make any manual changes to really interact with that binary at that object file level. So the first thing we did was develop the deep cut plugin, which is a Ghidra one-shot analyzer that runs deep cut against the current program that you have open. And the result is that every function gets assigned a module name in its namespace field. So it's implemented in Java, it's a Java analyzer, and it generates a function call graph that calls Python to run the deep cut machine learning model that Robert just spoke about. And then that model can also be used by other tools to generate JSON formatted function call graphs as well if need be. So once you're in Deep Cut, the next step is to use the CodeCut GUI plugin, and I'm just going to go over some of the core functionality that we've implemented. So the CodeCut GUI plugin is meant for reverse engineers to really be able to visualize and work with the Deep Cut result, and again, make any of those modifications at that object file level. So that's doing things like namespace modifications as in renaming, resizing, combining, or splitting. It's also modeled after the built-in Ghidra symbol table, so if you all are familiar, it has a lot of the same functionality, so symbol filtering, you could use regex or text, renaming or deleting functions, and then we can also drag and drop between the different namespaces. So in the case that Deep Cut may have assigned an incorrect module name, you could just drag that function into a different part of the table, and it will update the table as well as the namespace field of that function accordingly. We've also implemented some module name guessing functionality, so this is using Python and natural language processing to analyze all the different strings in the functions of a module, and it will come up with a best guess name for that module. This is really dependent upon the strings that are available in the binary, so it does have the potential to do things like picking up source file names, but that's not always the case. And then we also have a number of export options, so the users can actually use that CodeCut data. The first one is exporting a module map, so that is all the addresses of the object file boundaries as well as the names that the module name guessing stuff has picked up. And that could be useful in the case if you're working in a team or something and you have the binary at a good spot. You could export the module map, someone else could import it, and it will update their CodeCut table accordingly. You can also export as C, so that will take either an address range or a single function, and it will output those functions or that function as recompilable C source code, which Jonah will get into in a little bit. You also have the option to output an entire module, so that is all the recompilable C source code for all the functions in that module, as well as its relinkable elf or .o file, which Josh will speak about. And then lastly, we've also implemented a way of improving the Ghidra source to assembly mapping, which is used by things like the highlight functionality. So if you highlight some source code, it will highlight corresponding assembly language instructions, and a lot of times that's just like a single instruction or a couple. So we've actually improved that mapping to attribute more of those assembly instructions back to their respective C source code, and we're outputting that as dwarf information that comes with the ELF file, and it will map between that relinkable ELF file, its assembly instructions, to the line numbers of the recompilable source code to aid with any type of patching. And then we have a demo that Okay, yeah, so this is just to show what CodeCut looks like and how you use it. Is that?
Did it?
Yeah, it's fine.
It's going. Okay.
Yeah. Okay, so you open it like any other Ghidra plugin using the Windows tab, and once it opens, the first thing I'm going to do is set the Python executable path. The module name guessing stuff does require Python 3, so I'm just setting that in the tool options. And then the next thing I'll do is kick off the module name guessing. So again, this is going through all the different strings in the functions and coming up with the best guess name. In this case, I believe the binary had a lot of debug strings, so it's actually able to pick up all those source file names. And once it finishes running, it's going to update that left column of the table. I'm not sure how well everyone can see this, but that top one says object 1, and once it finishes running, it's going to update to cbc.c. And then I'm going to demonstrate the other functionality, so dragging and dropping. Say you've done some REing and transport handler doesn't look like a CBC function. You could drag that into a different namespace. You can also do things like splitting. I'm going to combine them into one larger namespace, or renaming. If the module name guessing stuff doesn't pick up anything useful, you could also, based on your own work, come up with your best guess and rename it in the table. And this step is really important for doing things like outputting relinkable .o files. So yeah, definitely take full advantage of all the different things that you could do to get those boundaries as close to correct as possible. Yeah, so this is just me renaming. And then the last thing I'm going to do is, once I think I have this in a good spot, I'm going to export the module map. And then once that exports, I'm going to open it to show what's inside of it. So again, that's the addresses of those object file boundaries. So it will append a .map file, and that is what CodeCut will take if you import it as well. And then in there, there will be the first column of addresses you see will be the module base. Then the next column is the module size, and the last is the names that are picked up by the module name guessing stuff. And now I'll pass it to Josh.
So that was a real quick overview. Thanks, Amanda. And there's obviously a lot of, if you're just reversing, so Josh is going to talk about unlinking. If you're reversing, there's actually a lot of benefits that gives you to be able to kind of work at the object file level. But we're not going to go into that whole lot. We're going to kind of talk now about, Josh is going to talk about unlinking here.
All right. Yeah, so my name is Josh, and I'll talk about the unlinking of the binaries. And so first, I'll just say, like, so why do we need to unlink binaries in the first place? And Ozzy kind of alluded to it earlier, right? So, like, there hasn't been a lot of gains in the embedded space, and so the ability to unlink libraries gives us a better way to maintain code for embedded devices. And there are two different scenarios, which I think Ozzy kind of alluded to earlier as well. Right, so let's just say APL developed something, you know, but we lost the source code for the device, or we lost the build environment. Making changes to that firmware device becomes a lot more difficult now. Similarly, say if we bought a firmware device from a vendor, and that vendor either stopped supporting the device or they just went under for some reason. If we want to reuse any libraries from that firmware, it's a lot more difficult to do so. Additionally, if we want to patch or modify the existing firmware, it just becomes it's just a lot more difficult, or sometimes even impossible. And so then we kind of think about moving towards maintenance chains instead of your standard build chains. And then, so Ozzy had the image earlier, right, where you write your source code, you compile and you get all your object files, and then you have your executable that you then ship out to your customers. But the ELF format is meant to be transformable in that you should be able to go from one view to the next. And I'll talk about views in the next slide, but the idea is that you should be able to go from this thing that you shipped out to something that's a little bit more manageable to maintain and modify. And so then we can start asking questions, so like what information should we save from the compiler, from the linker, so that transforming these binaries can be a little bit more tangible and maintaining them is a little bit more easier. And so here's just a brief overview of the ELF file format, and I won't bore you with all the details about the ELF file format. There's a lot of information on the web, but the main thing I want to talk about is the different views, as I mentioned earlier. So right, there's the linking view, which is when you're how to build executors, right? You have all your .o files that you then compile and link together to create your execution view, which then you would, that's how you, when it gets loaded into memory, CPU executes instructions, et cetera, et cetera. And so the linking view can contain something called relocations, and if you don't know what that is, it's like when you're writing your code and you call printf. The printf functions as an external library call. When you compile it to a .o file that's relinkable, that it doesn't know where that printf function actually lives. So when it has a relocation to say, at some point, tell me where this printf function lives so I can then execute that function. And that's what the loader does when you actually load it into memory. And you can see in the image on the right there that the code and data blocks are very similar, and that's kind of where I mentioned that the ELF format is meant to be transformable. These two, the data blocks are kind of parallel to one another, right? So like when you're executing the code, they're called them segments, but when it's actually in a file, they're called them sections. And it's this transformability to kind of make this work somewhat possible, that we can go from this big executable to then try to unlink it to a smaller library that we can then relink with other libraries that we've unlinked with our code or with actual valid GCC compiled libraries. And so here's the general approach of our code here. So we want to use Giggles API as much as possible because CodeCo is built using Giggles, and so we thought to have more continuity, we thought to use Giggles API. So the idea is to take a fully linked binary and unlink a single library from that, and the unlinked library should be transparent, right? So like if you use readelf or object dump or you want to compile it, it shouldn't be any difference between a library that I unlinked or a library that GCC then compiled. It should all just work together just fine. And so we wanted to use the output from CodeCut, obviously, so like the script will take in the library boundary. So let's say library starts from this address and ends at this address. And my script will take that and then gather all the relevant symbols and data and try to create a valid elf file. And Amanda mentioned that it is important to get those boundaries correct and all the functions correct, because my script doesn't attempt to make any corrections to it. So if you miss a function that should have been in that library, if you try to link it, if another library depends on that function, it's not going to be able to find it. So you need to ensure that all the actual functions are contained within the library, and that's the beauty of CodeCut. You can actually go and change things around as you see fit. And so here's just a general high-level algorithm of the actual unlinking of the library. So the first thing I try to do is, if it is an actual full-length executable, I try to parse the elf file to see are there any sections and data that I can just sort of take as a starting point to sort of get myself kicked off here. And so I just check for are there any is the elf header, can I look at the different number of sections, the different types in there, and I use that just to sort of get a bucket of different things that I can then go and modify and change later on. If that information is available, then I just sort of build everything from scratch. Then there's the gathering of all the symbols, and again, this is all dependent upon the libraries being, the boundaries being defined very clearly. And the script will go through and find all the different bytes, and it'll try to symbol relocation data as well. So if it uses Giggles cross-reference APIs to determine if a library is actually, or a function call is within a library module or if it's external. So I determine that to say if I have the library boundaries and I say, okay, it called function X. If function X is not within the boundaries, I determine that as external library call. And then I say, oh, okay, well, zero out the bytes there, and then there will be a relocation at that address. If it's within the boundary, I'll just say, okay, cool, I don't have to do any more work. And then I go and modify the section headers, right? Because obviously, if I'm taking a big library and a big binary and bringing it down, the size of the .text section is going to change, the size of the actual offset of the sections are going to change as well. And so I have to make sure that all that is correct, because if it's not, then ELF is going to, or like GCC or readelf is going to say, hey, this does not look right, something's wrong. And I ran into that error quite a few times, and I had to actually go and debug actually like the readelf program. And so then after I get all the data, I'll have all the things that I need. I just write all the data to a file and kind of a sequential format to where it makes sense. And the thing that's really nice is that it doesn't really matter the order in which you write things. As long as the ELF header is up top and you tell it where everything is supposed to be, it's going to be just fine. But let one byte not be in that right place and everything goes to crap. So that was kind of irritating, but I was able to work through some of those issues. And the input and output to the script is very simple. So on the left-hand side is what the script does. It just pops up a list and says, hey, what module do you want to export? And this list is taken from the namespaces that CodeCut generates, and the user, they select a module. No other input is required from the user at this point. Just you better hope that you'll have all the functions in there, otherwise it's going to be not a great unlinked library. But assuming that you have everything correct, it will generate a valid ELF file. And as you can see from the right-hand side here, I meant to highlight it, but let's see, hopefully you can see that. This is a relocatable file, and this was taken from a larger binary that we had in our possession. And so that's about all I have, and I'll give it over to Jonah.
Hello. This thing? This thing. Okay. So I'm going to talk about the recompilable C portion of CodeCut, which was implemented with the Ghidra Python API. So the idea of it is that the Ghidra ingests a binary and then outputs some decompilation. And if you take a look at it, it's actually pretty close to being recompilable with a few issues. It's designed to be readable, not recompilable, but with a few modifications, you can actually get it really close or there to being recompilable. So there's a few issues, and I'll talk about them now, and then I'll talk about the solutions to those issues, and then some work that's still left to be done. So the first issue right away is that there's external symbols, functions that are defined elsewhere. And you don't really know where they are just with a binary or the information that you're given. And then another weird, like, Ghidra-specific thing is these things called Ghidra intrinsics, or internal decompiler functions. And what these look like are like the concat function, which is like concat31, which essentially just smushes 2 bytes together and then outputs like the concatenation of those inputs. And then the subtraction function, or subtraction, which is a truncation function on 2 inputs. And then there's the issue of undefined types. So if Ghidra doesn't know exactly what a data type is, it'll just say it's undefined. And it generally knows what the size of it is, but if it doesn't know what the exact type of it is, it'll just output undefined. And so if you try to put that binary, or put that C through something like GCC, it'll complain. And then lastly, there's like a very strange memory syntax that Ghidra will output. It'll do something with like offset and numbytes. And what this means is it'll try to access a property, generally in a struct, and it'll try to access it at offset, and then the length of it in numbytes. So there's an example here where it accesses the 4th byte in read frame copy, and it has length 2, and then assigns that to the 5th byte in CTS data. So these are things that if you were just to put this C code directly through a compiler, it wouldn't actually output anything for obvious reasons. And so some solutions to that are the external outputs. We can just find all of the external functions using the Ghidra Python API, and then prefix that with extern in a ghidra.h file. So we're basically saying let the linker handle that. And then we can define the Ghidra intrinsics, the like concat and subfunction, as well in a ghidra.h file. We do the same thing with the undefined types. Since we kind of know what their sizes are already, we can just essentially put them in there. And then the weird memory syntax can be translated to something a lot more readable. So if we observe that there's any of these like unaligned memory accesses, like here, we can translate it to something a lot more sensible. We know that since the size of the byte is 2, it's probably an unsigned short, and we know exactly where it's trying to access it because of the offset. So you can see that it's accessing the 4th element in reframe copy, it's casting it to an unsigned short, and then passing it to be the, or assigning it to be the 5th element in CTS.data. And then that's kind of how we handled the issues back here. And there's a few unhandled things. So firstly, we don't actually do anything with stack canary checking yet. So the underscore stack underscore check guard, we're not disabling that. And then there's another issue as well where if you've ever looked at decompiled C code with Ghidra, you'll often see this weird ampersand stack OX offset thing. And generally what this means is that the decompiler is recognizing that there's a stack access, but it's not really, it doesn't really know like where that's coming from. And so what this generally is that there's a mismatch between what Ghidra thinks that the input parameters to a function are and what's actually being what's actually happening. And so this generally means that there's an error and the user has to fix the exact input parameters to the function. And so yeah, that was the recompilable C part. If you want to download CodeCut, it's here at this URL, github.com/jhuapl/CodeCut. And it supports Ghidra 10.1, 5, 10.2, and 10.2.2. I guess I'll give it to Ozzy.
That's all we have. Okay. Thank you all. Yeah, I was going to say this is a good time if you want to get up and stretch and like get your arm moving. Thank you for sticking through it. A very technical talk on a Sunday morning at ShmooCon. I know Sunday morning's always rough because of the Saturday night parties, but we thank you for being here, and we'll take questions, I think, if we have a couple of minutes.
Thanks for doing this, so none of us have to. It's pretty badass. And then my question is, what's next for you guys? Do you have any other projects related to this?
So the comment was, thanks for doing this. You're welcome. The the other question was kind of what's next for our team, what are we working on? What we're working on with the rest of MineSite is we've also been working on extending the Ghidra decompiler with Python extensions so that you can do Python passes in the decompiler. Jonah really wanted to talk about that today, but we had to kind of keep it to one theme. But we're hoping to, that's something we're also hoping to kind of open source. We're actually trying to, we'd like to work with the Ghidra team to get that upstreamed. But that's something that it allows us to do a lot of like research within the decompiler. So that's the, I guess that's kind of the main next thing that our team's working on. Question over here. Yeah, question is obfuscation techniques that CodeCut would have trouble on, and you're definitely right. We generally, when we're using CodeCut, we're usually working with just commercial firmware, right? So when you develop commercial firmware, you're not trying to be real tricky. You're trying to just make everything work, compile and that kind of thing. But you're pointing out a really good thing, which is that if you play any kind of compiler tricks, you can really mess things up. You can really mess disassemblers up, right? So if you don't, if your compiler doesn't follow the standard ABI, passes parameters in weird ways, you can really mess with the disassembly. So if you have some kind of like packed malware or something like that, yeah, CodeCut's really not the tool for that. It generally works pretty well on commercial firmware because, like I said, those are usually very well, organized. They behave well, let's say. Cool. Well, we'll hang out for a little while and love to talk reversing with you. Thanks, everybody.
All right, I have a piece of swag to give away. This is one of the inflatable solar lamps that we did a few years ago. I will toss it and try not to kill anyone. A couple of announcements that we have are that, first of all, we couldn't do this without you. We really appreciate you being here. It wouldn't be a con without you, and we do it for you. So if you have feedback on things, send an email to feedback@shmoocon.org. So again, feedback, we read them all. We really want to make this a better con every year, so let us know what you liked, what you didn't like. We still have t-shirts and swags available for a donation at the registration desk. So if you still want t-shirts, you want one of the bags that we have from previous years, etc., they are still up there. And if you lost something, check the lost and found also at the registration desk. There are things that are there, so if you are missing something, just ask if they have it, because they might. Are we ready to go? All right. So I would like to introduce Casimir, who is a security researcher. He does vulnerabilities at Trellix, and he's going to be talking to us about how to escape the tar pit and secure your supply chain.
Thank you. So, as he said, welcome to Escaping the Tar Pit and Securing the Supply Chain. Thank you, everyone, for showing up after hotel checkout. All right, so let's go ahead and get started. Who am I? I am Casimir Schultz. I'm a security researcher over at Trellix. If you want to contact me about this research, other research, or just in general, you can just contact me at casimir.schultz@trellix.com or my Twitter, which is abraxas7331. I would also like to give a shout out to Charles McFarland, who is a researcher at Trellix who helped me a lot with this research. All right, well, let's go ahead and get started. So before we can get to the fun stuff, the patching and the in-scale GitHub work, we actually need to talk about what exactly is the tar file vulnerability. And before I go into what it is and how to exploit it, I'm going to give you a bit of history about the vulnerability. So the vulnerability was first discovered in 2007. And so I just want to reiterate, it was an end day. It was not a 0 day I discovered. And despite being discovered in 2007, there was not really any discussion on how to mitigate this vulnerability until 2014. In 2014, we started seeing some discussions on GitHub. However, the discussions were more focused on whether or not this vulnerability should even be fixed rather than how it should be fixed. And because of that, we don't really see much action on it until 2018 when a pull request was submitted. However, in 2019, that pull request was, in the end, not merged because of failing test cases and some other issues as well. Then in 2021, somebody refiled the issue, and then after no response came in 2022, they re-reported the bug. All right, so what exactly is CVE 2007-4559? Or from now on, I'm going to refer to it as tar file because that's just a mouthful. Nobody wants to say that. So the CVE is actually a path traversal attack in the extract and the extract all functions in Python's tar file module. So the tar file module is actually part of CPython, so it is built in and part of every single Python installation that you have. And then the way that the vulnerability works is there's extraction on file metadata that has no validation. What you actually see up here on the screen is the vulnerable piece of code within the Python tar file code. And this is actually a snippet of code from the extract function. The extract all function actually uses the extract function as well. And as I outlined here, we have the os.path.join on the path and then the tarinfo.name. Path is the path that you are trying to extract your file to, and then tarinfo.name is just the piece of metadata from the file. So that's where the file name, and that's where you can actually add whatever you need to use for the path traversal. So let's talk about actual exploitation. What you see here on the screen is actually the piece of code that you need to exploit the tar file module. And as you can see, it's pretty quickly and easily created. And most funnily, it's actually, you can use the tar file module itself to exploit the tar file module. So as you can see here, we have a little piece of code. We import the tar file module. We have a function called change name. And then we open a new file called exploit.tar. And then we add our malicious file. So the malicious file can be whatever you want to overwrite, since we have path traversal leading to a file write, which you can then use to exploit whatever project. And what you see that might be a little bit special here is we have the filter, and that filter calls a function called change name. This is part of the tar file module. It allows you to add a filter that you can then change metadata with. And as we can see here in the change name function, we add the ..//, which is how we do path traversal. So the malicious file is not going to be actually opened up in the directory you want, but rather in the parent directory of that. And that can get pretty bad going forward. So now that we've talked about the vulnerability bit, let's talk about the scale of the vulnerability, since obviously we need to talk about the scale so that we can figure out why we actually had to patch. So some of these numbers might look a bit confusing. Some of you actually might recognize some of these numbers. The 1,000 is the search result limit for GitHub. So if you've ever tried to search code on GitHub, you've probably seen that after 1,000 search results, it says, I'm not giving you any more, which is not great if you're trying to patch everything, right? Or even just trying to figure out what exactly is vulnerable. However, we saw on the side that there were about 300,000 code results for this vulnerability. So we saw that there were around 300,000 files that contained the tar file module, since that is what we were looking for. So we actually contacted GitHub, and we're trying to work with them for this vulnerability to find out the true scale of the vulnerability. And I woke up one morning with an email from GitHub and several gigabyte file, which was quite surprising since I was expecting about 300,000 file names and repos. And we discovered that there's actually 2.87 million files on GitHub that import the tar file module, which is pretty big. And then we did a bunch of work, a bunch of deduping that information, and we discovered that there's around 588,000 unique repositories that import the tar file module. So that's 588,000 files that we had to search through. And obviously, no one wants to do that by hand. I am definitely a lazy person, and if I can, I will automate, which I'm betting most of you will as well. So we decided to build a tool, or just have a tool to do that. And this is actually how I built Creosote. So Creosote is the tool that we built in order to actually scan for this vulnerability in code bases. And then later on, I actually modified Creosote to do the automated patching, which I'll talk about later in the talk. So let's go ahead and talk about the requirements. So what did we need Creosote to do? So we needed an automatic way to scan vulnerabilities over millions of files, right? Because we had millions and millions of files. We also needed to have confidence levels attached to each result to filter out what manually needed to be looked through. Because obviously some pieces of code are going to be more likely to be vulnerable while others aren't. And nobody wants to look through every single potential vulnerability. You want to have marked which ones to look at, which ones maybe you look at if you have time, and then also depending on what type of work you need to do. For example, security researchers might only care about vulnerabilities that are most likely vulnerabilities. Well, if you're trying to patch your code base and make sure there's no more vulnerabilities, you're going to look at everything, even the false positives. And then finally, we needed a way of receiving a report that pointed directly at the vulnerable line of code. Because obviously, just telling you a repo is vulnerable isn't going to do much. You can start looking through there, but you still have to do a lot of work, which the tool should do. And as I mentioned earlier, I'm pretty lazy. So the first thing I decided to do was try to find another tool that did what we needed. And I came across a tool called Bandit. Bandit's actually a pretty popular tool, and I bet a fair number of you use it. But for those of you that don't know, it's a tool that's designed to find common security issues in Python code. So exactly what we needed to do, right? So the way that Bandit works is it processes each file, builds an abstract syntax tree from it, and then runs appropriate plugins against the abstract syntax tree nodes. So those plugins are actually plugins that you create, so you can easily create your own plugins and find vulnerabilities that you discovered in other code bases using Bandit. And once Bandit has finished scanning all the files, it generates a report for you, and that report can be modified via the plugins as well, which is pretty much everything that we thought we needed. So we tried using the tool to actually write some stuff, and we realized, oops, we can't use it. Otherwise, we wouldn't have generated our own tool. So there were two main reasons why we couldn't actually use Bandit. The first was that Bandit looks for a specific node. So it looks for an attribute node or a call node. And then after that, you can do your check. However, with the Python tar file vulnerability, which I'll talk about later, we have multiple different nodes that then lead to the vulnerability. So to go down, you would have to do a lot of extra work. And with Creosote, we were actually able to bypass that work by checking at a specific node and then backtracing back to check the other nodes, which was a lot more efficient. And that brings us to our second point of we had to actually hack at the functionality of Bandit to be able to look backwards, and that's something that we just didn't want to do. And the reason for that is actually because the way that Python abstract syntax trees work is parents isn't automatically on the node, which I'll talk about how we bypass that later. So then once we saw how other tools did it, we saw what we needed to do, and we updated our requirements. So we added a new requirement that we needed to add backtracing to figure out the context of the archive extraction. It wasn't enough to know that we had an archive extraction. We had to know if the code actually does try to do any checks on it, or if there's anything else done. So before we can get to the really fun stuff that you guys are all here for, I'm going to give you guys a bit of background on abstract syntax trees, especially abstract syntax trees in Python, especially for those of you that may not have used them before, or if you just need a quick refresher. I know a lot of times, I'll know a topic and then I'll forget about it as I go. So for those of you that haven't worked with abstract syntax trees before, the way it's set up is you have a simple, if you have something like this is an expression in Python. We have 2 times 7 plus 4. So obviously, we need some way to represent that in an abstract way. And the way that abstract syntax trees would work for this is you have binary operations. So you have the left node, right node, just like a binary tree. And then you have the operand. So for this one, since there are 2 different operands in here, we have to figure out what we're going to do there. So for our tree, we're first going to have the plus, which means that on the left-hand node, we're going to have another node. And then on the right-hand node, we're going to have the 4. So as you can see here on the left-hand side, we have another node that's another binary operation, and then on the left we just have the constant, and then from there we also have 2 and 7. So that's just a high-level overview of how abstract syntax trees work, and let's actually talk about how they work in Python now, because that's a bit different, and obviously there's going to be different specifications and weird tweaks for the code base. So in Python we have these major groups that I'm actually going to go through and talk about a little bit. But the way that the nodes are split up are into these 7 major components, or sorry, 6 major components. And before I continue there, I would like to give a shout out to greentreesnakes.readthedocs.io. It is an incredible site that actually has a lot more detail about how all the nodes work, and the Python documentation actually references this site and says, hey, if you actually want more information, go here. They did a lot better than us, which was actually pretty nice to see that they actually gave a shout out to them as well. All right, so let's go ahead and get working here. So most of you have probably worked with literals. You see what those are. So you have the constant and num string, list, tuple, and then the one that I can't say the shortcut for because I'm on air, but dictionary. And then let's actually go through and discuss how these nodes work in Python. So obviously with a constant, you need some way to store the value. And the constant node is going to have a value attribute which holds the Python object it represents. So for our example earlier where we had the node with 4, that is a constant. And then if you have dot value, that would actually be the value of 4. As you can probably guess, with constants, the values can only be primitive types. So you have numbers, strings, and then the none type as well. Next, we have variables, which I don't even have to explain to you how important variables are, especially when you're doing source code analysis, right? So the most important component of the variable that the node holds is the name. That is stored in the attribute for .id. And then what's also really interesting is that it stores the context. And for those of you that may have worked with Python bytecode, you might recognize load, store, and delete. It's not too important for this talk, but it was important enough that I wanted to give it a shout out while going through this. Python bytecode has different ways that it handles variables. So you can load a variable, you can store a variable, all of that. And when you actually have the abstract syntax tree nodes, you can actually see exactly how that's handled. So if you are working on something else that's using the Python abstract syntax tree, it is actually very useful if you need to do that sort of analysis. Next, we have expressions. For our expression, the 2 times 7 plus 4 would be a good example of the first expression since we didn't return it or do anything or sign it. So it would appear as a statement, but it is truly still an expression. And then, as you saw earlier, we had the binary op, where we have the op, which contains the operator, and then we have the left and right nodes. And then most importantly, for Creosote itself, we have the attribute node. So the attribute node is important because you have a value, which is another node, but you have the .attr, so attr, which is a string giving the name of the attribute. For our example, we have tarfile.extractAll. So .extractAll, that extractAll component would be the .attr, so that is why that is a very important node. Next up, we have our statements. For our statements, you probably recognize most of these. We have assign, we have import. All of you probably realize that import might be important when we're trying to figure out which files, import tar file. And these are pretty simple. You have just targets on a sign, which tells you the list of nodes. And then once again, you have your value, which tells you the actual value that it's set to. And then import, we have a list of names that are then used for the aliases. Next up, we have control flow. And for this slide, the ones that are actually important to us are for and with. And I know you're probably wondering why they're at the bottom then. That's because the if statement actually does a bit of some weird stuff. And that's, if you've ever worked with Python, you've definitely used elif, right? And the way that the if statement works for the control flow in the abstract syntax node is there is no body for elif. So you have your body and you have your or else, which both contain a list of nodes. And it's important to note that those nodes are in order of the source code appearance. So when you have your if statement, you have a block of code. Everything that's in there is then is a node in the body or else. And then the elif is actually another if node within the body. So that's how that works. It's just a little thing, but it is fairly important and can be frustrating when you're trying to build a tool and all of a sudden, parts are missing. So for us, the important components are the for and the with node. For for, once again, we have our targets attribute, which contains all the variables that the loop assigns to. We have iter, which contains the item for the that's going to be looped over. And then once again, we have the body or else. Some of you might be wondering why for has or else, and that's actually because in Python, you can actually have an else statement on your for loop, which when you're trying to do source code analysis and you don't know things like that can be fairly interesting. So definitely had some mistakes happen there. We also have our with statement, which has an items of with items nodes. And the way that with statements work, for those of you that may not be too familiar with that, is you have a code block. So you have the with statement, which opens up a context. And then you have an indented code block that uses that context, and then that context automatically closes afterwards. So for example, opening a file, the file is automatically opened as soon as you leave the indent. And then finally, we have our function and class definitions. These are pretty self-explanatory, so I'm not going to go too in-depth with these. Function def is defining a function, and class def is the class definition as well. So then now we can actually get to the interesting components. So in order to actually write a tool that scans for vulnerabilities, you need to actually know what you need to look for. And for our case, we had two major formats for this vulnerability. We had what we called the extract all vulnerability, which is when the tar file gets opened in a with statement, and then after opening, the tar file is extracted using extract all within the first block, or the indented block. And then the second major vulnerability that we saw was what we dubbed the extract in a for loop, or the for loop extract. And we loop through the get members function, which is a function for tar file objects. And what it does is it gives you all the files within the archive. And the way that that works is during the for loop, we run through and extract and run extract on each object. Together, these two vulnerabilities constituted about 90% of the vulnerabilities, or even just vulnerable lines of code that we saw. And that's a pretty large number, especially since it's two very, very specific examples. So you might be wondering, how does that happen? And that's because in almost every single tutorial that we saw, and I mean really almost every single tutorial, even on Python's documentation itself, Stack Overflow, Geeks for Geeks, Tutorial Point, every single one actually shows you how to extract the tar file incorrectly. So it will extract, but it is vulnerable. So it's just something to keep in mind when you're using a site like that for something else. So that is why we saw the same, which was actually great for us because we only had to really code for those two specific vulnerabilities. So now that we know about what we're checking for, let's talk about the internals of the vulnerability. I'm going to slow down a bit so that we can actually really talk about this. So the first thing that Creosote does is when you run it, you give it a directory to scan. Our directories were just, we had all the repositories in one major directory, and then we just pointed it at that directory and let it go because we wanted to let it run overnight or over a few days, more over a few days, and I'll talk about that later. But the way that it works is it takes the directory and it recursively goes through all the files in the directory that you're given. Once it finds all the files, it goes through and it sorts all the py files, and we use glob and iglob for that. And then it looks for anything that imports the tar file module. The reason for that is because there is a fair amount of overhead turning source code into an abstract syntax stream, and sorting through all the Python files first, and then all the files that only include the tar file meant that we only had to run our code analysis on the files that might actually be vulnerable. And we actually did not use the abstract syntax tree to find the import, and the reason for that was because that would have been a good amount of overhead turning something into an abstract syntax tree, but we used string scanning, and the reason why it was so fast was because imports are almost always going to be at the top of the file, so the string was going to be found very, very quickly, because normally, you know, just scanning the first string is not very quick. So once we actually found all the files that contained tar file, we actually wanted to start scanning them. So what we did was we started feeding the source code to our analyzer class. And the analyzer class was just an abstracted class that is provided by the tar file, or by the abstract syntax tree module, and it's a node visitor. So if you've ever worked with abstract syntax trees before, you have all the different types of nodes, and the node visitors allow you to create abstract functions, so override functions, and then for each node. So if you want to visit the attribute node, you'd override the visit attribute node, and then anytime that it sees an attribute class, you just go into there. From our analyzer class then turned the source code into an abstract syntax tree. Then it walked through the tree and added the parents to each node. So this was the important step I mentioned earlier for how we could add backtracing. And the reason for that was because the nodes by default do not have a parent node attached to them. However, when you initially walk through a tree, the function that does the walking has the parent and the current node, so you can then attach the parent back to the node and then reference it later on. And then from there, we started actually visiting the nodes. And then, so as I mentioned earlier, we only had attributes because we were checking for the extract all and the extract functions. So all of the nodes that we needed to visit were attribute types, which meant that when we actually hit an attribute node, we could then perform our checks, and that's all we had to do from there. All right, so let's go ahead and let's actually walk through the code. I'm going to apologize. There's a lot of code. I split it into 2 slides, but it's still going to be fairly small. But don't worry, I highlighted everything for you, so you should still be able to see. All right. So you might have noticed here we have the extract all. So this is already within that overridden function for the attribute node. So we're already assuming that node is going to be of type attribute. So we have .outer for checking here. So as you can see here, the first thing that we do is we check to see if the attribute is extract all. So as I mentioned earlier, one of the things Bandit did was you had to actually look for a specific node and then go down. So if we had done this with Bandit, we would have actually had to check for the with block and then go down, try to find the attribute node within the with block, and then there's a lot more with blocks that use open than there are just nodes that call extract all, because it is really, you know, just for extraction. Once we have that, you can see here we check to see if the parent's parent. I know it's a lot of parents, but that's just because of how it's nested. That is always going to be that way if it's in the indentation, so you don't have to worry too much about things changing, which is pretty nice. But we check to see if it is a with block, and then we go through, and here you can see that we check to see if that with block contains an open function. And the reason we check to see if it contains an open function is because that was kind of the template that we saw for this vulnerability a lot of times, and we want to make sure that the file was actually opened there and it's not just an extract all that might have been something else. Once we see that there is a open function, we go through and we check to see if the the second argument in there is going to be R. The reason we check the second argument, not the first, is because the first is always going to be your file, and then the second is going to be if it's read mode, write mode, all of that. So we check to see if it's R. However, we also check to see if there are no arguments, because we have the R is actually setting mode, which is an optional parameter, which means that it might actually be set directly with mode. And so we do a check here as well to see if mode is set to R. And then there's later on another check to see if the variable isn't set at all. So if args is not set at all on the second one, that means it's automatically defaulting to read as well. And then here we have our extract check. And as you can see here, we have extract, where we check to see if it's extract. However, you see that we do a lot more checking here as well. Also, don't worry, these slides are all online and the code is public as well, so if you can't read the slides here, the code is available. It's all commented exactly the same. Don't worry, I didn't publish code without commenting. That would be a little bit cruel. But anyways, so here we check to see if the actual node for the attribute class is also a call function. And then because the extract function has to be an actual call, otherwise you can't extract. But then we check to see if it actually has parameters. Because there are a lot of other extract functions out there, and a lot of them will just extract the object that they're attributed to rather than have something passed in. However, with the Python tar file module, you do actually need to have an object passed in, so that's why we perform a check here to make sure that there is actually an object before we do other checking, which cuts out most of the false positives in the checks here. Then we go through, and again, the parent, and we check to see if that is a for loop. Because the extract vulnerability, that templated vulnerability we saw, was within the for loop. And then once we do that, we have another check here to make sure get members is in the for loop. Now, a lot of you might be noticing that I stopped using abstract syntax trees here for this section, especially the get members. And you might see that I have ast.unparse. And the reason for that is because for loops can get pretty complicated pretty quickly, and things can be set differently. You can assign multiple items at once. However, Python's abstract syntax tree has a .unparse function, which takes whatever node you have, and only that node, and then transforms it back into source code. And what we can then do is, rather than trying to traverse that node and going down, we can just directly do a string check to see if the getMembers function is in there, which actually sped it up a lot, which was nice. We then later on use that and see if we have R in open, and then we do another check as well. So you can probably see we have a bucket where if R is in that string, we attach it to vulns, otherwise we attach it to probable vulns. And the reason for that is if there exists an open function in a for loop and you don't see R specifically, it's most likely still going to be opening for read mode. And it can either be that the variable isn't assigned, or the variable to mode is directly assigned via a parameter as well. Because it doesn't have to be set directly to an R. The parameter can be set to, or the argument can be set to R and then pass through later on. So now that we've talked about how we actually detect the vulnerability, especially over all those lines of code, let's actually talk about how our confidence levels are set up. So as I mentioned earlier, our confidence levels are used to determine which lines need priority during the checking process. Because you only want to really check something if it's really vulnerable. And if you were paying attention to the code earlier, you might have noticed that we have 3 different categorizations for this. The first categorization is vulnerable. Next we have probably vulnerable. And finally we have potentially vulnerable, which I know aren't the most descriptive. So I was trying to make an internal tool that would check ours, and then we ended up publishing it because it was working. So let's actually go through and explain how those work. Anything that's marked as vulnerable, especially if you're scanning your own code base, you definitely need to check out. Anything marked as vulnerable is pretty much guaranteed to be vulnerable. There's a few small cases where that's not the case, which I'll discuss later, but for the most part, you need to check it. Anything marked as probably vulnerable is something that had all the specifications for vulnerable, but had some sort of modification. So in the last slide, I showed you how if it doesn't have open and R, it went from vulnerable to probably vulnerable. And that's because it most likely still is vulnerable. However, we can't guarantee it. And we didn't want to do patching on anything that we couldn't guarantee that was vulnerable. So anything marked probably vulnerable still, most likely is vulnerable. And then finally, we have our catch-all, which is potentially vulnerable. And the reason why we added this bracket was if there was an extract all or an extract, we still wanted to add it to potentially vulnerable because we were checking our own internal code and we wanted to make sure that there were no vulnerabilities in our own code bases. All right, so now that I've talked about the tool, let's actually talk about how the finding summarization is done. Since I mentioned we need some way to detect the vulnerabilities, we need some way to show confidence levels, and then we need some way to actually show the vulnerability. So this is actually a live result from URH, which is Universal Radio Hacker. This has already been disclosed, and we have a blog post that was originally released when we discovered the vulnerability. Since then, we have a lot of updated information since the patching process started in September, but actually finished about 2 weeks ago because of the large amount of patching we had to do. So if you are curious about how we actually exploited URH using the Python vulnerability, you can read the blog post. You can just Google Trellix tar file, and you'll most likely be able to find it. Anyway, so let's go through and actually discuss what you see here. So as you can see, Creosote gives us a nice summary up top telling us how many files had vulnerabilities. It then gives us an overview of how many vulnerabilities it found, how many probable vulnerabilities it found, and how many potential vulnerabilities it found. What we then also have is we have it going through every single file, giving us the full path to the file that's vulnerable, as well as telling us how many vulnerabilities it found and what line numbers it found. So on file operator, we can see that we have a vulnerability on line 224. So you would go to that file, line 224, and that's actually where you would find the vulnerability from back then. It's been patched by now. The way that Creosote works, if there's multiple vulnerabilities in a file, it will just do a comma-separated list rather than just saying found vulns on line and keep going, because that would be pretty annoying over a course of time. All right, so obviously we can do stuff better. I was writing this tool by myself. I was writing it pretty quickly, and it was not meant to be scalable. It was meant for this one specific purpose, and there's other tools that are already scalable. Those exist. I'm not going to try to write a tool that everyone can use for everything it wasn't intended for. However, there are still lessons to be learned. I'm not perfect. I didn't know everything. I learned a lot during this process. The first was that I definitely needed to have better finding summarization. So it worked for what it needed to be. But especially when I started going through the potential vulnerabilities, it got pretty tedious pretty quickly going through and actually checking every single file. So one of the things that I thought I could add better here was add a context in the summarization. So you add the vulnerable line of code, and then you also give context of 2 lines before, 2 lines after, or something like that, just so you can go through really quickly in the report and say, oh, that's definitely not vulnerable. That's not even the tar file module. Or you can actually go through and see, hey, that might be vulnerable. Let me check it out. Another thing that I thought might be pretty useful is you can add hot links for the numbers. So especially depending on your development environment, you can pretty quickly code up something where if you have a number, you press it, and immediately takes you to the exact line of code in the exact file, opens it up, everything for you, which would be very useful, especially if you're combing through a lot of these. I also thought it would be nice to add object tracking, especially through functions. I've done a lot of work with abstract syntax trees in the past, especially with deobfuscation, and one of the things I worked on there was actually tracking objects as they're passed through functions. As I mentioned earlier, sometimes you have arguments that are then used, and what you can do potentially is you can track back through the functions all the calls that go to that function, and then see if any of those are set to R, possibly create import chains that directly tell you where the vulnerability starts and then where it ends up. And then we also want to add more checks to bring some of those potentially vulnerable to possibly vulnerable or vulnerable, because we did make a fair generalization because a lot of the vulnerabilities were the exact same vulnerability. However, you can definitely add a lot more checks and find more with a higher accuracy. And then finally, what would also be nice would be to add a way to analyze better what happens between the open and the extraction of the actual file. And as I mentioned, most of the vulnerable ones were vulnerable. However, there were rare cases where they actually performed some sort of check on the file between the open and extraction. This was less than 1% of the files that we saw, because any ones that actually did checks, they did it during the extract all process. So that's why we checked that extract all didn't actually have anything special there, because when you do extract all, you can specify which members to extract. So what they normally do in the extract all is they set the members to some sort of function that then goes through and checks the members and then passes them in, which is actually what we do in our patch. So now that we know what we can do better, we've talked about the tool, let's actually talk about the real meat of what's happened since September and now, which is patching by the thousands, or actually tens of thousands. So the first question is, why did we decide to patch? It's a pretty big amount of work, and we had a lot of people get pretty angry with us, especially small repo owners. Why are you spamming us? Stuff like that. And the first reason was we wanted to raise awareness about the issue. This issue had first been discovered in 2007 and had pretty much been forgotten about by the community, as you can see by all the tutorials that show you how to incorrectly do it. As I mentioned earlier, Python didn't even know whether or not they wanted to patch the issue. And the reason for that was because they wanted to remain compliant with the actual specifications of the tar archive. Since the tar archive does allow you to do path traversal, they wanted to make sure that they didn't change anything and break stuff, which I'll talk about later as well. So we saw that an upstream patch was likely to be delayed, which is not good considering that 61% of the projects that we hand-checked were vulnerable to the tar file extraction. So for the ones that we checked, I went through and I personally checked every single Python project on GitHub over 5,000 stars. And of all the ones that imported the tar file module, 61% of those were vulnerable to the extraction, which is not great, especially considering what a lot of those projects have or are used for. So now that we've talked about why we decided to patch, let's talk about what to patch. So we decided that we wanted to only patch the extract all in the with block, because while the extract in the for loop was pretty common, the extract all did represent about 80% of the vulnerabilities that were out there. So, as I said, 80%. And then we only wanted to patch what was actually vulnerable. Nobody wants a bunch of pull requests to something that's not vulnerable, or not even the tar file module, right? So what you actually see here above is the actual patch that I wrote. So this patch is, I took some of the code and was inspired by the pip module, or not the pip module, but pip, the source code, where they actually do it correctly because they know it's an issue and decided to fix it. Especially since if you've ever, cloned something, or not cloned, but used pip, it's all tar archives, which is a lot of fun. And the way that it works is you see here we run absolute path on the directory we're trying to extract into and absolute path on the file we're trying to extract. And what that gives us is it gives us a common prefix, so we know where it's trying to go. And the reason why I did it like this was because I knew I was going to make mistakes, and I knew if I was trying to make a filter, somebody would come up with some insane way to bypass that filter. And then another reason why we did this was because we listened to Python, we listened to the community, and I wanted to make a way where you still had path traversal, especially within the directory that you wanted to go into. But it was still secure in the fact that it did not go outside of where you wanted it to go to. So if you did want path traversal, you could just do root, and you'd still be able to use it exactly how you were planning on using it. All right, so now let's actually talk about applying the code patch. So there's two main ways that you can apply a code patch. The first is abstract syntax trees, and the second is just source code patching, at least for this project. However, both have some drawbacks. So while abstract syntax trees allow you to actually replace nodes fairly easily, it can be pretty inefficient because whenever you create a new node or replace a node, you have to re-index a lot of things as well as add information. And the second main drawback is that you have to convert the tree back to source code. And there are a lot of tools that do that. However, every time you convert something back, it does it in exactly the format that the source code converter did. So that means all the formatting that's already in the file is going to be gone, and it's actually going to modify the entire file rather than just what we wanted to patch, which means it's very annoying when you're trying to go through and figure out what was changed for a merge. And it can also mess up whatever conventions they have. The second approach I mentioned was actually modifying the source code directly, which means you have to start parsing a lot of things. And that can get pretty tedious pretty quickly, especially since everything has different ways that it's set up. Another issue is we're working in Python, and you have to worry about indentation, which is lovely, especially spaces versus tabs, and that just becomes a mess. So what I decided to do was leverage abstract syntax trees to actually apply the code patches. So we were able to actually pull a lot of the information directly from the abstract syntax trees nodes. So we got the line number from the node. We were able to get the variable names, the parameters and arguments, all of those from the different nodes that we already had in our memory that we were using to check for the vulnerability. And we were also able to pull the indentation from the abstract syntax tree node. And then finally, once all the data was grabbed, we were able to rewrite the code directly. Since we knew the line number, we could just remove the line, take our code patch, apply all their parameters, all their indentation, and then paste it directly into the code without modifying any of the other files. So obviously, we had issues. Former developer, so I'm used to these. Some of these were quite surprising. The first was there were actually so many files that contained the tar file module that GitHub was not able to use their new search functionality to get those files for us. And they actually had to go through and comb through a bunch of old data sets to figure out which files contained the tar file module, which was a lot of fun for them and for us, and they told us a few stories about that. And obviously, some of those repositories didn't exist anymore. So when we were trying to clone or do forking and all that, things broke. Of course, there's also edge cases that you never expect. I had a pretty large batch running, and I woke up in the morning to everything having completely crashed and having lost the entire night. And that was because a developer decided to put an emoji in a file name, and I had not anticipated that at all because, Who would? And then obviously speed issues. So I mentioned Creosote was originally written just for finding the vulnerabilities. So we had quite a few speed issues that required optimizations, but if any of you have ever written tools, you know optimization is really the fun part, especially seeing the numbers go down. And then finally, we had hard drive space issues. And the reason for that is because we had around 350,000 of those 600,000 repositories that contain the tar file module were actually vulnerable. So a lot of them weren't like truly vulnerable, so we only had to, and it was a small number that we actually had to locally save off, but we wanted to make sure that all the patches were done locally and saved locally so we could audit them before we start, annoying everyone with a ton of pull requests that are wrong. And storing, 60, 70,000 repositories takes up quite a bit of space. I will talk about how we solved that in a minute, though. So solving the speed issues. As you can see here, there's quite an overhead to even get the first file. And the reason for that is because when you're iterating over millions of files, it takes some time to sort through those files. When we first used Creosote, it was actually using glob rather than iglob. And glob goes through and collects all the files. However, it has to load them all into memory first. So when you have that many files, it takes a while to load into memory. iglob, however, is a generator, so it runs asynchronously, and we were able to, as you can see, basically instantly get the files. We also did some changes with in-memory versus file I/O. So rather than reading the file each time from the file system, we stored it in memory and passed it along. And then originally, as I'd mentioned earlier with Creosote, we go through the stages, find all the files, then find which ones have tar file. We changed it so that it would go through all the files, find a Python file. If it had tar file, we would immediately check it and patch it, which not only sped it up, but what it also did was it allowed us to, if something did crash, like with the emojis, we didn't have to restart the entire process. Thank you. So we went from about 300 seconds just to even start to about instantaneous, and then we went from about 5 to 6 seconds per file to around 2 seconds per file, which was a pretty good speed up. So as I mentioned, we also had the disk space issue. So what I decided to do was I created this new way to actually store the patches. So we have our patch directory, which has all our patches. We have a directory number. The reason for that was because a lot of the repositories had similar names, so it was pretty hard to have some way to do that. So we just indexed all of them and then referenced them later. We also have matches.txt, which looks like this. There's just a separation that I put in there, which would hopefully never show up in a repository name. We went through a few of those, as you can probably guess. And then there is the relative path to the file in the repository, and then the unique ID. And you can see that we have the original folder and the patch folder, and both of them have a file with that unique ID. And the reason for that was because we saved off the patch file and the original file. And the reason we did that was because when we were doing our forking, we checked to make sure the original file had not changed since we did our patch. And we did that because we didn't want to regress the file that we were merging into, because that would really just annoy a bunch of developers. So now that I've talked about how the patches work, let's actually talk about doing all this in scale. So we had a fairly automated process. There were 6 major steps, which you can read, and those were split into 2 components. We had cloning, patching, and saving, and then forking, committing patches, and then pushing and doing pull requests. The first 3 steps were done on one side, so that was all done offline. So we cloned all the repositories, we patched them, and we saved them locally in the setup that I just told you about. And then after that, we went through and we did everything later. For a few reasons. 1, so we could audit, and 2, so we weren't just patching a bunch of random repositories without actually having told the world that this is an issue, because then people might see it and start going to other things. So let's actually go through and run through the code for each of these components. And I tried being nice and making snippets of code that were nice and small, so you had a little bit more text. So this is the first snippet. This is to actually clone the repo. You can also see we have an insert auth here. And what we do here is we take the authentication token, which I was luckily smart enough to remember to X out. Otherwise, you would have all seen our authentication token, which wouldn't have been great. We have our GitHub username, and then auth is just a string combining those two. Insert auth puts them into something you can use. And then in clone repo, we have clone from, which luckily enough, there is a pip module named git, which actually does cloning for you, which is great. And then you can see that we return the object that returns at the end there. Next, we have fork repo, which actually uses the object from the clone repo. This is just a string name, sorry. But the first thing that we do is we add a random component to the repository name. As I mentioned earlier, we do have a lot of repeats in repository names, so we added 4 random characters to the end so that we didn't have overlap. And since in the end we had an estimate of 60 to 70,000 that were truly vulnerable and trying to patch, we figured that 4 characters would be enough because we didn't want to add a ton and have a ton of overhead. Then in the headers, we add our authentication token. And then we have our JSON object, which is just the new name in the name field. And then we actually have to use requests directly to send that. So we had to reverse GitHub a little bit. It's not too hard because you can just use developer tools, luckily. But for this, there is no library that actually does the work for you, so you do have to directly do the requests. Next, we have our committing and our pushing. Committing is nice and simple because you can once again use the git pip module. Here you just add your name, you add your email, you add all the files or whatever files you want to add. We added them all since we actually wanted all the files we modified to be there. And then you go through and you commit. Our commit message was just saved off at the top of the file just to make the code a bit neater. And then pushing is pretty similar. You have the remote branch, and then you actually just do git push, which is really nice and simple. And then, there we go. And then finally, we have creating the PR. So creating the PR, we once again had to reverse how GitHub does it a little bit and do requests directly. So up here, what we do is we grab the prefix and just split it out to get the name. Here, we once again add the authentication token to the headers. And then here we add the data to our request. The 2 important components that you have to look at are title and body. So for the title, it's obviously whatever title you want for the PR. However, body is important because body is actually the markdown body of the pull request. So when you go on GitHub and you see the long list, that's actually going to be what gets populated by body here. So you do have to make sure that whatever you have in there can actually be passed in as a string and is marked down. And then finally, we just do a simple post request, which goes through and does the request, and that's how we did the pull request. So now finally, let's actually talk about the results of all this. It finished about 2 weeks ago. Trellix is releasing a blog post on Monday if you are interested in reading more about the whole process and the results of that, but I'm going to give you a quick overview. In the end, we were able to send out 61,895 pull requests. This took about 3 months to do, so it was a lot of fun. We did have some pushback. However, we had a lot of notable projects actually accept the pull request and actually thank us. So I'm just going to go through and talk about some of those projects real quick. The first one, which I definitely am most proud of, is MobSF. Most of you, or a lot of you, if you've ever worked with Android, you've probably used this tool since it's an amazing tool, security tool for analyzing Android, just anything Android. And they actually merged our pull request and sent us a thank you message. We also had Open3D Engine, which is the largest open source game engine, accept our pull request as well. And we had a few people from Amazon, since there's a few Amazon people actively working on it, send us thank you messages as well. And then another notable one is MonAI, which most of you probably don't know. However, it is a medical open network for artificial intelligence. And what's really notable about this diverse group is we really impacted every single industry. You have security, you have gaming, you have medical and AI, and all of these were impacted by this Python vulnerability. We also had a few people who didn't want to merge our pull request directly, but instead contacted us and asked us to check if the changes they had done were truly secure. One of the most notable ones and a group that was actually very fun to work with was Conda. So Conda, thanks to our pull request, found that their package streaming was vulnerable to the tar file. And with package streaming, that's a bit remote. So that's not great if it can be remotely accessed. So we were able to work with them and patch that as well. Thank you so much. This was my first talk at a major conference, so thank you so much for coming. If you have any questions, now's the time. Yes. Yeah. Yes, so he just asked, after we had scanned and everything, how we went from having it locally to actually going through and doing the pull requests. So the way that that worked is we just had a little bit of code that recloned the repo, which is why it took so long. So it cloned the repo, checked to see if the original file was still the same, which there's tons of different ways to do that. We just did a text comparison because we wanted to make sure nothing got wrong with like hashing. And then we just overrode the file and then did our commit and pull request. So it's just a nice, simple process. Yes? Have you guys updated all the tutorials yet? So he asked if we've updated all the tutorials. Sadly, no. We have, this is why we did it. People are talking about it. I've talked to a few people at the conference and they actually, said, hey, I actually read your blog post, which is a great feeling. So hopefully we can get this updated, but no, as of now, I don't think they're updated. Yes? No worries. I'll answer the first one first. So he asked if Python has responded and actually, fixed it or started fixing it. We actually worked with Python when we first released the research. I was talking with them. I sent them my patch. I was explaining how the patch worked and all of that. There was discussion for a few months. However, the discussion has pretty much died down once again. So it is actually still in Python's tar file module. And the discussion really went from, started with how are we going to patch this to back to are we even going to patch this? Because it's, it is valid. You can use tar files that way. So right now the discussion pretty much has died down. Did you remember your second question? All right, I have to stop, but if anybody wants to come up to me afterwards, I'll be here for a few minutes, so if you want to come talk, I'll be here. Thank you so much again.
That was fantastic.
Thank you.
So at this stage, since we're here, I can extract the source medium. Right there. That goes with me.